Good afternoon and welcome to another exciting soils episode. I'm here live in the ESF TV studio. Pretty cool, huh? And I'm going to talk to you about soil colloids today. And first, I have a few announcements that we always begin each class with announcements. And of course, you're already aware, but the reminder, there is no lab this week. Hooray, this allows you to get ready for the CEC lab in the coming week. Of course, this lecture and the next lecture sets us up for that, for the foundation to be able to do that. Exam 2 is Wednesday. We'll have a little bit of an interruption in the schedule with an exam. And remember, no calculators. There'll be calculations, but these you can use your hand calculator, right? Because everything is divisible by 2 and by 10. They'll all be simple math, but there will be math and no calculators. So last time, where were we at? We talked about wetlands and hydric soils. We then segued into soil temperature. We talked about solar radiation and soil temperature, and that led us into the ideas, the concept of the factors that influence soil temperature. And we talked about thermal conductivity, and we talked in some detail about thermal conductivity and how different physical properties influence thermal conductivity. And we closed that session with a little bit on frost heaving, and that wrapped up soil temperature. And that pretty much takes care of soil physical properties, and now we're ready to embark on the chemistry of the course. Ooh, but this will be a chemistry as it'll be understandable as we talk about soil colloids. And so first, thinking about the excitement of colloids. So this picture kind of, it shows a rather striking place in a golf course, and this is there was a lost golf ball, and this came out of the New York Times. It was some 8 or 9 years ago, but it's kind of neat. But here they are playing golf, and of course, if this is worse than a sand trap, right? Because the golf ball kind of disappears. So then the reason here, of course, is this is a clay soil and colloids dominated. And colloids have this ability to expand and contract. So they have these crazy physical properties that really have quite an impact on the soil. And we're going to look at that in detail. Okay? And so there were humble beginnings. So this was it's kind of interesting. Back in 1850, there were a couple of scientists that leached ions through soils, right? And so they noticed and they measured what came through. The sulfate and the chloride passed through. But the cations, calcium, magnesium, and the other things, other positively charged ions, did not. And so that began this long sojourn to kind of understand that and advance why do they have these observations? Why are the cations not coming through, and yet the anions are? And so that became to be an interesting question, and it wasn't until the mid-50s that we were able to kind of advance the understanding of that with the result of some X-ray diffraction. And at that point, we're kind of able to see colloid crystalline structures, and it started to put these things together, and then we started to think about ionic substitution. And this was a major advancement in our understanding, and it all started, way back from the 1850s. It took 100 years before we had these tools, and now they've continued to develop those tools. And now, of course, we have some very fine, high-resolution X-ray diffraction, all these nice electron microscopes, and it's quite an interesting world. Okay? So that's got us started. So let's kind of take colloids in an overview. We provide the overall context, the foundation for this next week or two. Okay? And the first thing about colloids, they're small and very small. And so what does this mean? The smaller they are, the higher the external surface area, specific surface. So each time we'll kind of illustrate that with a diagram, is that the smaller the particle gets, the more surface area. Okay? And here's an illustration. Here's a cube, and if I have it's just 6 centimeters, and look at it, 6 by 6 by 6. And if I split that, I now have another surface, and I add a couple more square centimeters for this cubic centimeter. Here's the volume, here's the area, okay, all the surface area added up. And I split it again, and so you start to see every time I split this cubic centimeter, I'm boosting the surface area, and boosting it rather significantly. And so you keep going and going. So as I continue to cut and cut and cut, I continually expand that surface area. So this is the idea of specific surface. And this is just the outside, the external. And it'll later on when we look at the structure of this, we'll get into the internal surface area. Okay? So what can we make a general statement? Okay? We can say the specific surface of colloids, the specific surface, this centimeter square per cubic centimeter volume, that for colloids, it's more than 1,000 times that of the specific surface of a sand-sized particles. And it's just beginning, and sometimes much more than 1,000 times. Okay? So look at the difference. These small particles of clays, 0.001, 0.002 millimeters in diameter, compared to sand, 2 to 0.05, and then this explosive increase in specific surface area. And here's let's further illustrate that. Let's go all the way. So this graph from the text, right, shows page 136, figure 410. This plots this specific surface area, and this is in cubic millimeters per gram, millimeters square per gram, surface area per unit gram, and it plots it by particle size. So we start out with small particle size, clays, and you'll note it's a logarithmic scale, and we have the clays, 0.002 and less. We have the silts, 0.05 to 0.002, and then the sands and the gravels. And we learned these particle sizes last time in physical properties. And so look what happens if we go all the way out here to the gravels, okay? Practically no specific surface. But as that particle size decreases and we get into the silts, it starts to go up. And then as we get into the clays, it explosively increases logarithmically. So there's a tremendous increase in specific surface, taking this single cube and then making it smaller and smaller and smaller and smaller. And so this is the key surface, specific surface. This provides the area for chemical reactions, biochemical reactions to take place. Hence, colloids have a huge specific surface and become extremely important in the soil chemistry. So what are the implications? So here, this was actually years ago, and this guy was a kitten. He's since old and passed away. But this would be a cat, right? But the implications are cation exchange, and not Bagheera, not that cat, right? But cation exchange. Cations, positively charged ions, okay? And these are adsorbed. And so these absorbed cations, adsorbed AD, right? Adsorbed, they exchange with cations in soil solution. So they exchange. And this is an implication of having the surface area. It's a pretty important implication. Let's illustrate that. We can illustrate that with a colloid drawn here by this rectangle. And you see this has negative charges expressed at the surface. And that's balanced with positively charged cations. So this negatively charged surface attracts or adsorbs, and that's adsorb, AD. It adsorbs these positively charged cations, so they're associated. So, and it's a unit charge. So charge per charge, cations are attracted to the negative charges on this colloid. And this shows potassium, magnesium, calcium, and hydrogen. It shows their valences. You'll know these valences by the end. Potassium +1, magnesium +2, and calcium +2, hydrogen +1. And this is balanced. So the positively charged cations adsorbed to the colloid balance the negative charge exerted at the surface. And this represents soil solution. So if we have soil solution, there's some materials out here, some hydrogen is floating around, maybe balanced by chloride or something else. And the idea of exchange is that these cations in solution can replace adsorbed cations and exchange. So these adsorbed cations, these hydrogens that were in soil solution, are now attracted to the micelle, the colloid, and they've exchanged, and calcium is going into soil solution. Right? This is an illustration of cation exchange. The exchange of cations, it was hydrogen in soil solution, for cations adsorbed. So the accounting, it's on a charge basis. Right? So a plus charge will balance a minus charge. So we like to keep track of this on a charge basis. And so we're going to introduce the units of charge for cation exchange capacity. So some further implications. We can measure the capacity of these colloids to store, to hold, to adsorb cations. And we call that cation exchange capacity, CEC. CEC, cation exchange capacity. Okay? And we could define that. So if I ask you to define that in a test, the simple, very exquisite definition is the sum of exchangeable cations a soil can absorb. This should be AD, adsorb, okay? Adsorb. The sum of exchangeable cations a soil can absorb, that is cation exchange capacity. We express it in the units of centimole of charge per kilogram, C mole of charge. So this is very important. Okay, it's not C moles, it's not centimoles, it's moles of charge. So get used to this. This is the unit for CEC, centimoles of charge per kilogram. Okay, we'll go through it and we'll get used to that. And particularly in the upcoming lab next week, we'll have a chance to work with this and do some calculations. So now we have to start somewhere. So we start with the unit name, centimoles of charge per kilogram. What is this? You might recognize this creature. It's a mole. Okay? But the moles we're talking about, it's a little bit different. Okay? The moles, in terms of chemistry, as we get away from the biology, this definition of a mole, and you'll recognize this because you probably had chemistry in the last year or two, the amount of a substance that contains 6.02 times 10 to the 23rd atoms. So you recognize this as Avogadro's number, 6.02 times 10 to the 23rd atoms. Right? And a mole defines the molecular weight. And so just basic chemistry, simple review, not this mole in the picture, but this mole in text. So mole, more or less. Let's talk about a little piece of a mole, or a centimole. So I put this in blue to highlight it, a centimole, to also show you when you're looking at C-mole, you're looking at centa, okay? Centa. And so we're in the metric system, thankfully, okay? So a centimole is 0.01 moles. Like centimeters are 0.01 meters, centigrams. So now we have a centimole. A centimole, and it took me away. But this is a centimole with a C, okay? 0.01 mole. Just something you have to know. You're probably already familiar with this. You've done metric system for your entire educational career. Unlike me, I came up through the old days of the English units, and it was for a while it was a bit of a struggle when I was 17 and 16, but apparently I've survived, and I'm now metricized. Not ostracized, but metricized. Well, some might ostracize me. Not you. And so let's think about the other fact about this. So we have a mole, 0.01 mole, centimole, but we have different valences. So all elements are not monovalent. They don't all have a valence of 1. And for instance, these are the ones we're going to be familiar with, so you'll know these very shortly. Potassium, +1. Calcium, +2. Aluminum, or as the Brits say, aluminium, +3. And silicon, +4. These are the valence states. Okay? And so when we're trying to think about equal charge, it's now important for us to think about these valences. So we like to compare on a charge basis. And so it's much easier to keep track of a charge and just replace one charge with another and worry about the masses later. And here's a rather simple statement. A mole of plus charge of X plus will replace 1 mole of plus charge of Y plus plus, which will replace 1 mole of plus charge of Z plus plus plus, and so on and so forth. So a mole of charge replaces a mole of charge. And that brings us to the SI unit, System International, for CEC. Centimoles of, this is a little bit messed up, it's centimoles of charge per kilogram. I get to play with my annotator. Let's see if I can do this, my pen. Centimoles of charge, right here. I must have misprinted, I miscopied that. Centimoles of charge per kilogram. Okay, and this C means charge. So this is important in this unit. This C is important, centimoles of charge. So this is the unit. It's not centimoles per kilogram, it's centimoles of charge per kilogram. So let's take that a little further. So we'll take a mole. A mole is defined by the molecular weight. I've abbreviated that as MW, molecular weight. The charge is defined by the valence. +1, +2, +3. So then we put those two things together to get to the idea of equivalent weight that you've known now since Chem 1. The mass of a substance that provides 1 mole of charge. The molecular weight divided by the valence. Okay? Molecular weight over the valence. And you already know this as the equivalent weight, molecular weight over valence. Now we have a way to keep track of charge, and we can convert to mass. We'll find this very useful later as we get to some of these calculations. But for now, it's just the facts, So how can we use this? So we want to convert mass to charge, or sometimes charge to mass. We need to go back and forth between these two. And so we could ask the question, and we will ask the question in lab and on exams, what mass of calcium +2 provides a centimole of charge? Okay? What mass of calcium +2 provides a centimole of charge? So first we have the molecular weight and the valence. We've got to get to the equivalent weight. So the first part of answering this question is to compute the equivalent weight. So 40 grams, the molecular weight, divided by the valence, 2. That's the equivalent weight, and this is the mass that'll provide a mole of charge. So let's run the numbers. This is pretty easy, right? We don't need a calculator. I could use my hand calculator if I had all my fingers and toes, and my buddy next to me and his fingers and toes or hers, and I'd have 40, so we use a hand calculator. So 40 grams over 2, molecular weight over the valence, okay, and that's equal to 20 grams. So we're computing a mole of charge. It's 20 grams of calcium +2 will produce a mole of charge. Now, we need to get the centimoles of charge. The concentrations that we deal with in the soil are smaller, and we'd like to use whole numbers or simple numbers that aren't millions of decimals long or millions of, not millions, but several decimal points short. And so let's convert this to centimoles, 20 grams per mole of charge. How do we convert this mole of charge to a centimole of charge? Okay. And so remember the conversion, okay, for centimole is 0.01. It's 2 orders of magnitude smaller. So if we have 20 grams per mole of charge, and I'm illustrating this with my old way of just canceling units. This is, I actually learned this in 10th grade, Mr. Britt, and it stayed with me for many years, and it has served me well, and hopefully will serve you well, but you already know this stuff. So 20 grams per mole of charge times 0.01 mole of charge per centimole, right, there's the conversion. 0.01 mole is equal to a centimole. And why did I set it up this way? I set it up this way because I want to have the same units here, right? Cancel out, I want to get to grams per centimole of charge. So lo and behold, 0.2 grams produces a centimole of charge. 0.2 grams of calcium +2. So that's our answer. 0.2 grams of calcium +2 provides a centimole of charge. We took the molecular weight, divided by the valence, and then took that times 0.01, or we divided by 100. Whether you're a numerator person or a denominator person. Non-denominational. Not really. So where did all those numbers come from? And so you've already learned that. You've learned how to look at a periodic table of elements, and it's arranged by groups in the metals. And so if we look at that group with calcium, we find here's calcium right here. I've expanded this piece over here. Right. Oops. Find my, there we go. I've expanded this piece here. And there I have there's sodium, potassium, calcium, and so forth. And there's where these numbers come. These are the molecular weights, okay, the mass. And so calcium was 40, right? Potassium's 39. And there's calcium, so I'm looking at this, and find my pointer. It's tough to see it on the screen. There it is. I'm drawing with it now. There's calcium. The molecular weight's 40. Okay. Then the atomic number, you learned about that, the number of protons. But there's the mass, 40.08, the molecular weight. Dun, dun, dun. How about potassium? What's the mass of potassium? And you can see that, 39.1, right? And you could go to any table and get these. And you've had to do this, I'm sure, maybe years ago or some of you last year, but probably forgotten it. But just a reminder of where these numbers come from. Okay, so that was a little bit of chemistry. So we were able to go from mass to charge. And now we need to think about the overview and put this back into colloids, because we're going to group colloids so we have some understanding of their different properties. So let's start with the organic colloids. Organic, and we know organic matter, primarily carbon, hydrogen, and oxygen. And so some examples, humic acids, they're just all types of organic colloids. And the primary feature of note is CHO, carbon, hydrogen, oxygen. So here's one example. This is a structure of humic acid, one of many colloids. And just pick it because humic acid is very common in soil, folic acid and so forth. And you see it's just largely carbon, hydrogen, oxygen, and there's a few amino groups. Okay? But primarily carbon, hydrogen, and oxygen. This represents an organic colloid. And just look at that a little closer, and you can see it. And of course, you'd never want to know this structure, but it is an example of a structure, one of many, with a lot of carbon, hydrogen, and oxygen in it, and one organic colloid. So these colloids, the neat property is they exhibit a net negative charge. And so the next question is, well, where do those charges come from? And so that's the subject of this piece. We differentiate these colloid types on the basis of net negative charge and how those net negative charges are derived. So organic colloids, this group that we've separated out, we've chosen to talk about first, the net negative charge is a result of dissociation of hydrogen. Okay? Dissociation of hydrogen. I keep losing my pointer because my eyes aren't as young as they used to be. Okay, there it is, dissociation. Okay, and so it's more than that. So that's the beginning, and that's very important. But now the question is, where do those hydrogens dissociate from? And there are three primary groups. Some of you I know stay in organic chemistry after I leave my class and Dr. Gu comes in. And I see him and I know he's teaching organics, so that means I know some of you are well aware of this and maybe some haven't had it yet. But there are three groups that dissociate hydrogen in these organic colloids. The first one's carboxyl. Okay, carboxyl. I'll illustrate each one. First I'll name them. The second, phenol hydroxy, and the third, the alcohol hydroxyl group. Okay, so these three groups, 1, 2, 3, I feel like I'm doing Sesame Street. These three groups serve as a source, a place where hydrogen can dissociate from. So you'll note hydrogen's positive, right, H+, and so if H+ migrates away, that leaves a net negative charge. Okay, fair enough. Let's look at that in a little more detail. Here is an illustration of a carboxyl group. Okay, so we illustrate these long chains with a C. Okay, here's the carbon, and this is the long chains with an R. R is a whole bunch of carbon this, carbon that, blah blah blah, ethers, esters, whatever. But at any rate, this trick here, the focus of the carboxyl group is this double bond O and OH. Okay, so this double bond O and OH just kind of resonates between these two, and as a result, this hydrogen on this hydroxyl is prone to dissociation. Off it goes. Goodbye. And when that happens, you're losing H+, and so you're leaving a net negative charge expressed where this once was. Okay, so dissociation of hydrogen from the carboxyl group, C double bond O, OH, and R is all the other stuff. Okay, this is the working end, carboxyl. Here's a picture of it. I know the professor before me after me has these models. I see him with these playing with his model sets, and so you may have seen one of these models. Here's the R, the double bond O, and then the hydroxyl, right? And this is in one of these ball and stick models, like some of the country western songs, My Ball and Chain. Well, and if you're in organic chemistry, I guess it's a ball and stick. And the second, the phenol hydroxy group. So phenol is this 6-carbon ring with double bonds. Okay, on every other bond's a double bond, and they resonate. And the same kind of thing. This resonance of these double bonds gives some movement, allows some movement of this hydrogen to dissociate. So this H plus can dissociate from the phenol hydroxy group. Right? Phenol hydroxy. Here's the phenol. Here's the hydroxyl, phenol hydroxy group. And when that happens, bye-bye. Net negative charge expressed at this surface. And there's a picture of it, right? There's the little ball and stick model. And the third, the alcohol hydroxy group. So a simple, left the R out here, some chain of carbons, and then the OH, a hydroxyl. And that hydroxyl can lose, under some conditions, this H plus. When that happens, bye-bye. This net negative charge expressed. And that's it. They have these 3 groups, carboxyl, phenol hydroxy, alcohol hydroxyl, dissociation of hydrogen, generation of a net negative charge. How cool is that? And a picture of it. I didn't have a ball and stick model, but I did have the 3D model, but I have the kind of the loosely drawn this model. So, but at any rate, that's just another picture to illustrate. And so the neat thing about this, or the interesting thing about this, this is pH dependent. This will be pretty close to our last topic, our last lab, okay? And I haven't told you about pH yet, but we'll learn about this later. But pH, this acidity, for now, dissociation depends on the acidity, pH dependent. And so here's a picture, right? This massive humus colloid with the working ends. So here you'll recognize the phenol hydroxy group. Right? Here you'll recognize the carboxyl group. Okay? And let's see. And I didn't put in an alcohol hydroxy. Okay. So you'll recognize these groups and the pH dependent. So what happens? Low pH, high acidity. This dissociation isn't very large, right? Minimal dissociation under acid conditions, low pH. Very little, if any, dissociation. Okay? So if it doesn't dissociate, the CEC is low. You don't express the net negative charge. Okay? Acid conditions. Under high pH, okay, and this is backwards, and I apologize for this. High pH, low acidity, and this will become really apparent when we show you the scales. Okay, the dissociation is massive, right? A lot of dissociation when you have high pH or low acidity. Low acidity, Briggs. And so you have all these exposed net negative charge. And so this is a high CEC, right? Low CEC, no dissociation, acid. High CEC, high pH, low acidity. Okay. And so now when these dissociate, other cations are attracted to these surfaces, things like calcium, potassium, magnesium, and so forth. So this calcium here is +2. It's going to associate with 2 negative charges. There we go. This potassium here, +1, going to associate with that. Magnesium +2 is going to associate with these two. Okay, 1-to-1 charge. Here's 2, 1, 2. And that's cation exchange capacity driven by organic colloids. Okay, let's shift over to the mineral colloids. Okay, now we have a mineral structure. We're getting away from the CHOs, and we're going to talk about mineral colloids. So I just put that with a little Roman numeral 2 up here to differentiate. Not that it's one or just the second or more important than the other, but just to differentiate. Roman numeral 2. Here's a picture of one. This is a picture of this mineral colloid kaolinite. Okay, nice kind of cool looking crystals. And eventually we'll delve into this structure in great detail. But for now, just an illustration. Mineral colloid, this one's crystalline. Okay, so we start out with the crystalline silicate clays. Okay, so now the group is mineral colloids, and the first of these groups, the crystalline silicate clays, and we know these already. We know these are the aluminosilicates, right? Okay, these crystalline silicate clays are also referred to as phyllosilicates. You know, you had phyllo bread and the phyllo crust on some of those awesome pastries. And so here's, you wouldn't want to eat these. They aren't awesome pastries, but an awesome structure, this leaf-like phyllosilicates. And this example is kaolinite. And we'll know these in great detail later, but for now, here's a picture of a crystalline silicate clay that for this illustration is kaolinite, and this is out of the book. They're all out of the book unless I take them elsewhere, and I'll always show or point out the source of these things. Okay, so if we had crystalline silicate clays, you might be expecting that we'd have non-crystalline silicate clays. So still aluminosilicates, all right, silicate clays, but non-crystalline. They don't form crystals. And these range from totally amorphous to short-range order. Okay, so we call short-range order, I've got this in yellow, SRO, short-range order, and these come from volcanic ash and some igneous rocks. And these they have a little bit of order in the X-ray diffraction, but only in maybe one direction. Yes. So the general form of the non-crystalline silicate clays, aluminosilicate, okay, and these ones from volcanic ash usually have water in their structure. So a general form of the non-crystalline silicate, aluminosilicate right there, clays. Some examples, allophane, and you may recall back when we talked about parent material and I talked about volcanic ash, I specifically mentioned these two and I said you won't know what they are yet, but they become important later. Well, this is now. Now they're important, and we'll start to differentiate these non-crystalline silicate clays, allophane and amogolite. Okay? And we refer to these as paracrystalline. I think of, I always want to think of the Ghostbusters, but this is paracrystalline. And it's, again, short range order, but not completely three-dimensional crystals. So here's in a picture, nice little picture of allophane. Okay, and amogolite. So the thing about this, and why do I keep harping on allophane and amogolite? Well, these from volcanic ash, these have a very high capacity to adsorb phosphate. Okay, they can fix phosphate. And so allophane and amogolite, they can fix phosphate. That's later when we talk about nutrition, extremely important because volcanic soils have this ability to just make phosphate unavailable or kind of hang on to it. Here's amogolite. Okay, I had allophane before. Okay, and here's amogolite. These are just kind of cool. These are tubular. Tubular, man. Not that was I think some of the mole rats or something, but no, these are tubular in shape, right? So kind of one dimension, they have this, they're less amorphous, but they're so hence this idea of paracrystalline. Okay. And there's a color, they give this color to the soil. There's a volcanic soil dominated by amogolite, and I show that right here. Okay. Okay, so we have the crystalline and non-crystalline silicate clays. Okay, so we move to the next category of mineral colloids, still in the mineral colloids section, and the iron aluminum oxides and hydroxides. Iron aluminum oxides and hydroxides. What's missing? Silica. Okay, so dominated by iron aluminum, oxides, hydroxides, but now silica is not in the picture. And these range from crystalline to amorphous. They span the spectrum, all the way from shapeless to crystalline. Some examples, goethite, okay, FeOOH, and we've talked about this. It gives the soil these brownish yellow colors. There's a picture of it. You can see it, the colors that these goethite coatings leave, this brownish. Ferrihydrite, okay, ferrihydrite. Okay. This often precipitates, okay, a form of iron, and so you can see that, and sometimes you'll see these brown colors. This is ferrihydrite, this precipitating these mineral colloids that are iron hydroxides, right? Iron, ferra. And then hematite. Okay, hematite's the iron. This gives the soil red colors, this highly weathered red coating, hematite. So these are all iron oxides. Okay, of course they're non-crystalline to amorphous. They range in this, and what they lack is silica. Okay. And then we get to the aluminum. So these three are the iron oxides and hydroxides, and then the one in aluminum is called gibbsite. Gibbsite. I used to have a friend, a colleague, when I worked at the University of Vermont as a forest technician in the 70s, and it was Dave Gibbs. I always think of Dave Gibbs when I think of gibbsite, but he had nothing to do with soils. He was more of a forest management type person. And a picture of gibbsite, for what it's worth. So then we have these groups of the crystalline and non-crystalline silicate clays, and they're in the mineral colloids. And now we're going to take apart these crystalline silicate clays. We're going to, I call it deconstructing silicate clays. We'll explore their structure in the detail. So silicate clays, what are they also known as? We just talked about them. Crystalline silicate clays, crystalline, phyllosilicates. Okay. Crystalline silicate clays, the phyllosilicates. Okay, so you'll see both these terms. So we'll start at the beginning. What's the fundamental piece, the basic structural components of the silicate clays, the crystalline silicate clays? Okay, so we're going to need silicon and aluminum. And let's look at how those are arranged. So this is a picture of a silica tetrahedron. Okay, tetrahedron, four-sided, 1, 2, 3 in the back and one at the bottom. These are coordinated oxygen, and in the center is silicon. Okay, silicon, and this is all covalently bonded. This is the basic building block, the silica tetrahedron, one of the two building blocks of the crystalline silicate clays. Okay, the silica tetrahedron. The other piece of this, the other building block, is the aluminum octahedron. So here's aluminum and sometimes magnesium. We'll talk about why and when, but aluminum in the center, and this is coordinated with 6 hydroxyls, giving an 8-sided figure. Right? So if you roll this around like a dice, or blump, 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 it would be interesting. A dreidel, I don't know, but at any rate, 8 sides, and hence octahedron. Okay. And again, aluminum, sometimes magnesium, covalently bonded with these 6 hydroxyls, aluminum octahedron. So these are the two basic pieces, and we're going to take these two basic pieces, we're going to string them together, and we're going to build sheets. We're going to take essentially a model, and I don't have my model kit with me, but you could do this. You're already going to get enough models in organic chemistry the next class after me, so I left my models home, but I will bring in next class my own version of the model of these silicate crystalline clays. I think you'll be quite pleased with them. but that's for when I get back. So we can look at that in these ball and stick models in this faux 3D image, right? Here's a silica tetrahedron. Find my pointer again, right? And it's coordinated by 4 oxygens in this tetrahedron, and we can string them together, right? So we can have the silica tetrahedron, and we string them together, and we have sheets, and this repeats and repeats and repeats, right? So this is referred to as a tetrahedral sheet. These are covalently bonded. The silica in this silica tetrahedron shares an oxygen here, so they have this oxygen in common. And we can put these together, and covalently they have these beautiful silica tetrahedral sheets. Can do the same with the aluminum octahedral. Right? So here's an aluminum octahedron, and so each aluminum shares 2 of its neighbors' hydroxyls. Okay, these are hydroxyls. And we can string these together and make an octahedral sheet. Okay, so we're stringing together. So we're stringing together these octahedron, and we're making these covalent sheets. So let's take those and let's put those into a clay micelle. Okay, so a micelle. So one way to talk about a crystal, another word for crystal, is micelle. And this is the page 329 out of the text, figure 8.1. And in small letters here, you can see this unit here is a clay micelle, a crystal. And you see this 3-dimensional. And so now we look at this in greater detail, and we see it has individual pieces, and these are individual octahedral and tetrahedral sheets put together. And this is illustrating the difference between external surface area and internal surface area. So if we just look at this crystal, it has an outside, right? And so this is the external surface. If we go and look at the mineralogy of this crystal, we see that it is built to have a lot of internal surface area. In this, here's a little piece, so we expand this little piece, take this little nick out of it, and take a wider look at it, and we see surfaces in between these layers, okay, that have adsorbed cations, and also, not a picture here of water. So here we have internal surface. So it's not just the external surface. Okay, that's important, and that's already huge. But now we just add an order of magnitude. We have internal surface. Within this crystal, we have surfaces in between. That's cool. Okay. So that's a silica clay, and let's kind of revisit that. We have silica tetrahedral sheets and aluminum octahedral sheets. Now I'm going to add one more terminology, one more piece of terminology, dioctahedral and trioctahedral. Okay? And so aluminum, okay, dioctahedral sheet. And I'm going to introduce, and here's a picture of it. Okay? Here's an aluminum. There are 2 aluminum tetrahedra next to each other. They're sharing, okay? They're each sharing 2 of the adjacent hydroxyls. Okay? And so looking here, when I look at this little piece of it, I have 2 aluminums. And so if I look at the valence, the charge of that, +6, and that's balanced by the charge on the hydroxyls, okay, -6. All right, 2, 4, 6. So the net charge here is 0. Okay, a dioctahedral sheet dominated by aluminum. Dioctahedral, associate that with aluminum. Okay. What's the difference between that and a trioctahedral sheet? Well, I thought you'd never ask, so I'll tell you. So a trioctahedral sheet, okay, is dominated by magnesium. Okay. Now aluminum, if you remember, is +3, and you have to remember because we just talked about it. Magnesium is +2. So to balance this covalently, okay, it takes 2 aluminums +3, there they are there. It takes 2 of them, or we could kind of do a different crystal and use magnesiums. It would take 3 magnesiums, okay, trioctahedral sheet, 3. Now this isn't the charge, this is the number it would take to replace them, right? So plus 2 trioctahedral seat because you need 3 of them, plus 3 dioctahedral seat because you need 2 of them. And a picture, that same structure, and now instead of aluminum, there's magnesium, okay? And to get that plus 6 charge, it takes 3 of them, okay, to make it all covalently clean. Voila. Trioctahedral, uno, dos, tres. Dioctahedral, aluminum, 1, 2. 3 magnesium plus 2 satisfy the same charge as 2 aluminum plus 3. Okay, bottom line. So that's the way to remember dioctahedral and trioctahedral. Again, it's inverse to the charge, right? Okay, it's related to the number you need to generate the charge. Okay, so tricky at first, but after a few times on the flip cards, you'll have it. So that's the structure of these sheets, and now we're going to get a little wild and crazy, right? Now I'm going to talk about something called isomorphous substitution. Isomorphous substitution. So let's start with the definition. This wild and crazy, not wild and crazy, but kind of cool and interesting idea, supported by a lot of data, and we'll talk about. But at any rate, here's the concept. You can replace one atom by another of similar size, okay, without disrupting the crystal structure. So if I want to place a magnesium and replace with aluminum, after this crystal is all made, okay, you can replace that and the structure will stay the same because they're about the same size. Okay. And what happens is we find aluminum plus 3 replacing silica plus 4. Okay. And these are about the same size. And when we mess around, or so we re-engineer, or we don't re-engineer, I'd say the gods re-engineer this, okay? We have plus 3 replacing plus 4 in the same spot. We have a difference of 1 charge, right? So if this plus 3 replaces a plus 4, all of a sudden there's a minus 1, okay? And that's going to be expressed at the surface. The same thing happens in the trioctahedral layer, in the octahedral layer, sorry, magnesium can replace alumina. So this is in the silica, right? This is in the silica tetrahedral sheet, the silica layer. And in the aluminum layer, magnesium plus 2, 1 less, can replace aluminum plus 3. The net result, again, when this happens, is an unsatisfied charge. And so this is the concept, this is the definition, the description of isomorphous substitution. So here's a picture of it, right? The dioctahedral, okay, with isomorphic, so the dioctahedral aluminum. So if I take one of these aluminums out and push a magnesium in, okay, there is a net negative charge. And this is an illustration of isomorphous substitution. So the implication, the source of the net negative charge, so I'll write this down or circle it on the handouts, the source of the net negative charge on the phyllosilicates is largely isomorphous substitution. What was the source of net negative charge in the organic colloids? Dissociation of hydrogen. 2 mechanisms, 2 different colloids. That's the deal. That's why we're going through these colloid types, to understand some of the reasons behind and the thinking behind the mechanisms that generate net negative charge, as well as their physical properties. Okay. And I'm going to leave you with this slide for next time, okay? And we'll pick this up next, let's see, it's Wednesday, so we'll pick this up Monday morning. This is an illustration of the different phyllosilicates and their structures. So this shows kaolinite, 1-to-1. It shows smectite. It shows vermiculite. And it shows fine-grained mica and chlorite. These are all phyllosilicates, okay? But they differ in their structure, and as a result, they differ in their physical and chemical properties. We'll explore that next week. Have a good weekend and review the material in the website, and we'll be prepared for lab. And come prepared for lab and read the lab manual, and this will be much easier. Monday's lecture will set us up to further go ahead with this. So I hope you have a great week in the rest of your courses. And I'm going to have a great week because I'm at the Soil Science Society of America annual meeting where we live, breathe, and eat soils. It's just amazing. So my hope for you is someday you have the opportunity to attend the Soil Science Society of America annual meeting and perhaps even give a paper. And with that, I'll close and bid you adieu. And think small, colloids.